Have you ever tried to build something complex, like a Lego castle, but just by randomly throwing the bricks into a box and shaking it? You'd end up with a mess, right? For a long time, that's kind of how chemists made new materials. They'd mix ingredients and hope for the best, a process often called shake and bake. It worked sometimes, but it was unpredictable and inefficient. What if we could build materials with the same precision as an architect designing a skyscraper? What if we could place every single atom and molecule exactly where we want it to go? Well, that's no longer science fiction. Welcome to the world of reticular chemistry. This revolutionary idea was pioneered by Professor Omar Yaghi. He imagined chemistry not as a random mixing of potions, but as an act of construction. The goal? To design and build crystalline structures from the ground up, connecting molecular building blocks into strong, predetermined frameworks. Think of it like using molecular-sized Lego bricks, but instead of plastic studs, they're held together by powerful chemical bonds. This new way of thinking gave birth to an incredible new class of materials, metal organic frameworks, or MOFs. So what exactly is MOF? Imagine a structure made of metal ions, which act like the joints or corners, and organic molecules, called linkers, that act as the rods connecting them. When you put these two components together under the right conditions, they don't just mix randomly. They self-assemble into a highly ordered, three-dimensional lattice. The result is a material that is incredibly porous. In fact, MOFs are the most porous materials known to humankind. A single gram of a MOF, about the weight of a paperclip, can have a surface area larger than a football field if you were to unfold it. It's this mind-boggling internal surface area and the tunable nature of their pores that make MOFs so powerful. We can design the pores to be the exact size and shape to capture specific molecules. It's like creating a perfect molecular-sized lock for a specific key. This isn't just a cool party trick, it has game-changing applications. Let's talk about some real-world examples. One of the biggest challenges we face is clean energy and a clean environment. MOFs are stepping up to the plate. Because they can selectively trap gas molecules, they are being developed for carbon capture. Imagine power plants with filters made of MOFs that can grab CO2 right out of the exhaust fumes, preventing it from entering the atmosphere. They're also incredible for gas storage. A standard tank of natural gas for a car has to be under immense pressure, but a tank filled with a specific MOF can store the same amount of gas at a much lower pressure, making it safer and more efficient. The applications don't stop there. How about clean water? Researchers have designed MOFs that can pull clean water directly out of the air, even in the driest deserts. One device, powered only by sunlight, uses an MOF to absorb water from the air at night and then releases it as pure, drinkable liquid water during the day. This could provide water to millions of people in arid regions. They're also being used in medicine for targeted drug delivery and as catalysts to make chemical reactions faster and more efficient. And the reticular revolution doesn't end with MOFs. The same design principles have led to other amazing materials. There are COFs, or covalent organic frameworks, which are built entirely from light elements like carbon and oxygen. They are incredibly stable and lightweight. Then there are ZIFs, or zeolitic imidazolate frameworks, which are a subclass of MOFs with structures similar to traditional minerals called zeolites, but with far more versatility. Each of these materials offers a unique set of properties, expanding our molecular toolkit even further. What we're witnessing is a fundamental shift in how we think about creating matter. We're moving away from the old, trial-and-error approach and entering an era of chemistry by design. It's chemistry as architecture. We can now dream up a structure with specific properties for storing hydrogen, for delivering medicine, for capturing pollutants, and then select the right molecular building blocks and assemble it with atomic precision. We are becoming the architects of the molecular world. This is more than just an academic curiosity. It's the foundation for the next generation of technologies that will help us solve some of humanity's greatest challenges. The reticular revolution is here, and it's building a better future, one molecule at a time. Thanks so much for watching. If you found this fascinating and want to learn more about the amazing materials shaping our world, be sure to hit that like button and subscribe to the channel. Let me know in the comments which MOF application you're most excited about. See you in the next video.